Welcome to The Explainer. Today we're unpacking a genuinely fascinating architectural shift straight out of iScore AI Studio's Inkcloud project. We are going to look at exactly how their engineering team moved away from a super brittle, cloud-based LLM orchestrator and built a highly resilient local-first Unix Swarm instead. If you've ever dealt with AI agents just completely tripping over each other, or if you've watched your token budget go up in flames, this technical deep dive into their infrastructure is absolutely for you.
Okay, so let's just get right into the brutal reality of their postmortem. When the team first tried to build a high concurrency swarm for their Mark I conversion engine, they practically hit a brick wall. They quickly realized that the token cost, and honestly the cognitive cost, of babysitting this autonomous swarm was literally higher than if a human just sat down and did the work manually. The system was just too fragile to survive contact with reality.
And this perfectly illustrates why. You can see the context paradox here. Synchronous supervisor models suffered from massive context overload and what the team called gate paralysis. Because the system demanded a full health check on every single minor edit, those orchestrating agents were wasting a staggering 80% of their tokens just fighting legacy lint warnings. 80%! They weren't even writing code.
Real quick, here is our cognitive map for today's explainer. We're going from that initial orchestration failure straight into the Unix Swarm paradigm, the page-first pipeline, triple lock isolation mechanics, atomic queuing, and finally, swarm telemetry and recovery.
All right, Section 1, the Unix Swarm paradigm, yielding to the file system. Let's look at how the team actually rebuilt this thing, shifting away from that top-down command and control into a horizontal asynchronous Blackboard model using standard OS principles.
What's really profound here is the total architectural evolution. They completely ditched those centralized synchronous loops where a supervisor is constantly dictating every single move. Instead, they pivoted to a decentralized queue, managed entirely by autonomous peer agents that communicate purely through the file system.
Just contrast the legacy model with the new one for a second. In that old hierarchical setup, you had a hanging orchestrator process, literally just sitting in memory, burning through expensive API tokens while waiting for worker subprocesses to finish building. The new peer agent model? It's entirely asynchronous and bound to the file system. It scales by running independent worker-consumer loops right on the hard drive, completely isolated from each other.
Now, the secret sauce making all of this work is called the yield rule. Under this rule, an orchestrating agent like Codex acts purely as a planner. It breaks down a goal, writes the task assignments to a file-based queue as a JSON payload, and then, this is the crucial part, it immediately exits. It yields. The process terminates, which clears the context and saves massive amounts of tokens because there are absolutely zero hanging subprocesses.
Moving on to Section 2, the page-first pipeline, speculative triage. Let's see how this yields-based approach feeds into their actual processing pipeline, specifically their shift from a really inefficient block-first method to highly granular page-level processing.
So early runs exposed a massive bottleneck, granularity overload. The team realized that treating every single block of text as a separate translation unit was generating over 40,000 LLM calls for just one 2,000-page book, which is, completely unsustainable. So by pivoting to a page-first strategy, they achieved a massive 10x to 20x reduction in API calls. They completely escaped that granularity overload while actually maintaining a much better contextual flow.
Notice the selective escalation logic here. They aren't just blindly throwing a massive 120 billion parameter model at every single page. Instead, a really cheap local model like Gemma does a light pass on the clean, low-entropy prose. It's only when the system hits high-entropy layout pages, think complex tables or mixed media, that it selectively escalates the task up to high-parameter VRAM nodes running heavier models like Qwen.
Before we jump into the really dense isolation mechanics, I want you to consider the economic impact of this. Because this local-first swarm approach runs entirely on a heterogeneous cluster of their own hardware, it amortizes those hardware costs over time, dropping their ongoing token inference cost per million to absolute zero. Literally $0.
Section 3. Triple lock isolation mechanics, preventing data corruption. Okay, so with all these independent peer agents executing asynchronously and randomly grabbing tasks, how does Inkcloud stop the system from basically tearing its own file structure apart?
Well, to achieve true concurrent execution without nasty state collisions or data corruption, Inkcloud forces what they call a mandatory triple lock sequence. It's a brilliant defense-in-depth strategy that stops database locks and file overwrites dead in their tracks.
Let's break those locks down. First, agents are separated at the bare metal operating system level using dedicated PIDs inside a tmux session. Second, they're sandboxed into unique XDG data directories, which completely eliminates local SQLite database locking errors when a bunch of agents boot up at the same time. And third, every execution pod gets its own dedicated Git Worktree. That means zero index contention. They literally can't overwrite each other's commits.
By rigorously enforcing these 3 locks, they achieved incredible horizontal scale. We're talking 14 concurrent agent loops running across their hardware cluster, modifying the exact same repository at the exact same time without a single incident of file corruption. All right, Section 4, Atomic Queuing and Rollback File System Physics. Let's look under the hood at the specific script logic that handles task claiming, process execution, and error recovery, entirely without a centralized database backend.
The swarm relies on a male-deer-style queuing system. To claim a task, a worker basically executes an atomic rename, moving the source directory into a .partial state. It updates its UDP status to converting, runs that heavy lift conversion subprocess, and if it succeeds, it performs an atomic promotion to swap that partial file for the final output. The kernel's built-in file system physics is doing all the heavy lifting here.
But look, in distributed clusters, nodes are going to fail. They thermal throttle, drivers crash, it happens. So they built a robust rollback sequence. Every time the system starts up, a script automatically scans for orphaned work directories that aren't attached to an active PID. It atomically moves those orphans into a quarantine folder along with a forensic JSON report and runs a clean sweep so aborted claims don't leave annoying ghost packages hanging around in the output tree.
Finally, Section 5, Swarm Telemetry and Recovery, the UDP Bridge. Let's see how human engineers actually monitor and recover this fully asynchronous cluster using dedicated telemetry schemas.
The key here is what they call the durable handoff state, and the big takeaway is the total elimination of chat history dependency. When an agent gets interrupted, there is zero reliance on reading some massive, expensive chat log to figure out how to resume. Instead, every interrupted agent is forced to write a status.json file. This durable handoff state records exactly what was just finished, the concrete next step, any known blockers, and crucially, the exact terminal command needed to resume the process. To keep tabs on all of this, the Orchestrator daemon actively listens to a JSON payload being broadcast over UDP port 5053. That status.json acts as the machine-readable ground truth. But to figure out if a process has just silently hung, the orchestrator also checks the modification time of a progress.md file sitting in the agent's directory, which acts as a required ongoing liveness heartbeat.
So what happens if that heartbeat flatlines? Well, a really strict recovery pipeline kicks in. The task gets automatically shifted over to a dead message column. A human, or even an AI owner, is explicitly assigned to inspect the state, and the system forces a hard fork decision. You either do a reconstructed salvage, writing a new resume command, or you initiate a blocked kill to make sure abandoned work trees don't just linger in the void forever.
So, synthesizing all of this, what should you really take away from Inkcloud's project? It's that highly resilient multi-agent systems do not actually require magical, memory-heavy cloud orchestration platforms. To function reliably out in the real world, what they really demand is rigorous file system discipline and standard Unix state machine enforcement. The file system itself is the orchestrator.
Yielding control to standard file system physics literally unlocked true horizontal AI scaling for them. By respecting atomic moves and deep isolation, they built a swarm that actually fundamentally works, which leaves us with a really fascinating question. As we move further away from top-down AI babysitting, are these asynchronous, file-driven protocols going to become the ultimate standard for how we orchestrate autonomous software teams? It's definitely something to think about. Thanks so much for joining me on this explainer, and keep learning.